Hey everyone! Thank you so much for tuning in to the 104th episode of the Weaviate Podcast. I'm super excited to welcome Sayash Kapoor and Benedikt Stroebl from Princeton University. Sayash and Benedikt are both members of the Princeton Language plus Intelligence Lab, where they're the co-first authors of an amazing new paper, AI Agents That Matter. This paper dives into a super exciting concept of Pareto Optimal optimization of compound AI systems. This means not only optimizing the performance of the system, but also how much it costs to run it. So say GPT-4o costs $20 to write a blog post or review your pull request, whereas a system composed of Llama 3.1 AB models can achieve a similar quality output for $2 or less. This kind of idea of finding the right trade-off between how much these systems cost to run and all sorts of other details. The paper also dives into some really interesting observations about the state of benchmarking AI agents. All sorts of exciting things we'll dive into throughout the podcast. Sayash and Benedikt, thank you so much for joining the podcast.
Thank you so much for having us.
Thank you. Glad to be here.
Awesome. So could we kick it off with maybe sort of what led you to working on this particular category? I love the title already, AI Agents That Matter. It just instantly caught my eye. I almost want to have the title have a comma, like, unlike the systems that you're building, these actually matter. What drew your interest towards this area of research?
Yeah, it's a very interesting backstory. So actually, when we started working on this project, we didn't intend to write this paper at all. What instead we were working on was trying to reproduce existing systems for something we wanted to build ourselves. So we'd seen all of these systems perform extremely well, like complex compound AI systems perform well on coding benchmarks. And we wanted to basically use these systems towards our own coding problems. What we instead found was that it took us a long amount of time even to get basic reproductions of these papers going. And in the end, when we did manage to sort of end up reproducing these papers, reproducing these systems, each of these systems suffered from a number of issues. So we started with the human eval leaderboard and sort of went through like a few different agents, spending like a few hours on each implementation. And at the end of it, we basically realized that none of these agents are reproducible. And when we do manage to reproduce them, the performance does not really match. So I think that's when we decided to take a pause and look back at what we had found so far. And we realized that, the state of implementations of AI agents needs to drastically improve if they are to be useful in the real world. So that's when we started looking at this problem a bit more seriously. And that's when we sort of started doing this cost-controlled analysis, because one of the agents, I remember Benedikt and I were like in the lab late one day, and we realized that the agent had been running for like 3 days. And it had been running for 3 days on human eval, which is a set of like extremely simple coding problem. At that point, I could basically pay someone on Fiverr or something to solve all of these tasks, and it would probably be cheaper. And so this is where we started to think about what the real world utility of these agents really looks like.
Yeah, amazing. Benedikt, do you want to give a similar intro story of how you came to be working on this paper?
Yeah, so for me, it was actually started out with these, one of the late sessions that Sayash and I had in the lab, where we just literally wanted to use these systems for our own purposes, and then we just found out that, some agent code had bugs, or used different subversions of benchmarks. Like these are some of the more specific issues that we discover and describe in the benchmark, in the paper, sorry. But and then we kind of got more interested and looked into, okay, what can we do with this, and like is this a signal for the more general state of the field? I think another thing that kind of was interesting to us and informed then the baselines in this more cost control setting that we then used for our experiments was that we saw papers like the AlphaCode paper from Google DeepMind, for example, and saw that the pass at k is actually very different to the pass at one. So if you retry or sample from a model, right, and at some point you find a correct solution. So we hypothesized that this might also be true for these like more compound AI systems that you can also retry, but that might come at a lower cost than the existing systems.
Amazing. So maybe kind of the first question I guess I really want to kind of come into, if we could open up about the cost trade-off, performance costs. And you mentioned, I love the nugget in the paper about how you could just sample from the model, say 30 times. And I think there are a couple papers about like more agents are all you need, titles like this. I'll link them in the description of the video. But so maybe we could just start with this. There's also this inference scaling laws paper from Google DeepMind that's saying just use a smaller model, but run, say, 200 inferences per step of the compound AI system. And maybe quickly for our listeners, compound AI system is referring to breaking up the task into multiple stages. And so each stage you have a call to the language model. And yeah, so maybe if we could just kind of talk more about, I guess if we could just the Pareto optimal optimization, if we could maybe start at a high level, and then if we could get into technically how it works.
Great. Yeah. I mean, so basically what we were realizing was that when agents are being deployed in real world production settings, they're not going to be used hundreds of times. They're probably going to be used tens of thousands or maybe even millions of times if we look at applications at scale. And so even if cost is not really of importance to AI researchers, so they just want to break the state of the art, they're looking at samples which have, I don't know, a benchmark has like, let's say 300. Even the largest benchmarks for compound AI systems like SweBench have a few thousands of samples. They're not incentivized to decrease costs. They are, in the present state of things, they're only incentivized to improve accuracy. But now that we have evidence that more samples from a language model might be enough to scale accuracy, this one-dimensional metric of accuracy does not really mean too much anymore. Because in order to do better than an existing agent, in order to break the state of the art, so to say, all you essentially need to do is take a model, call it like a bunch more times, and then pick one of the samples based on some heuristics, right? And so just breaking state-of-the-art accuracy is not really enough to measure if you're actually making genuine improvements. So to test this hypothesis, we sort of implemented a bunch of these agents on human eval, and we found that it's true that a lot of the recently proposed agents do very well. But essentially, if we compare it against retrying multiple times, I think they lead to an increase of like a 0.1 or a 0.2% increase in accuracy, and they cost 5 times as much. Now, if you think about an ML engineer trying to deploy this model or this agent in a real world setting, the trade-off is obvious. The model that costs 5 times lower and has like a 0.2% accuracy hit is definitely going to be better. So in some sense, this is also a call for better baselines when we're doing agent evaluations. So if you are evaluating an agent, you have to evaluate it against simple baselines, for example, retrying multiple times. And then we sort of decided to go one step further. So now that we've started looking at this trade-off as a Pareto frontier instead of a one-dimensional metric, can we find agent architectures that maintain accuracy, but we can implement at a much lower cost? And one of the frameworks that both of us are big fans of is DSPy. So you've hosted Omar on your podcast before. You've hosted other people from the team, and we're likewise like really optimistic about what we can do using DSPy. So essentially, we implemented a new optimizer in DSPy to optimize for both cost as well as accuracy at the same time. So how this worked was in a traditional DSPy pipeline, you might try to optimize for accuracy using like a random search over few shot examples. Instead of just trying to optimize accuracy, we also changed the objective metric to also optimize for cost. So the agent was not just trying to find, or the pipeline was not just trying to find the optimal prompt, let's say for human eval, or the optimal prompt for a question answering benchmark. It'll also try to reduce the cost by decreasing the number of few shot examples, by finding examples that have a lower token cost, and so on. And what we found was that this very simple technique is already enough to reduce the cost again by half. So DSPy is already extremely cost effective because it allows you to find lower cost models like, let's say, Llama 370B, optimize them to work as well as much more expensive models like GPT-4. But then if you add this joint optimization of cost and accuracy on top of it, you can essentially reduce the cost by another 50%. And I think this is only the beginning in some sense. Like we implemented a very simple joint optimization. I'm sure we can do better if we put in more time and effort. But I think this just goes on to show that I think this is somewhat of a green field in terms of unexplored problems in agent optimization.
Yeah, absolutely. I couldn't agree more. It's such an interesting thing. I guess something we hear at Weaviate a lot. And I didn't mean to make it sound like this only works for compound AI systems. Even if you just have this kind of like hard coded retrieve and then generate question answering system, you still have the question of which model to choose. And then you bring up this really great point of how many tokens are used in the prompt, and particularly through the lens of the few shot examples. So maybe we could just unpack that for our listeners further. Let's just dive right into the technical details. So when we have this decision of few shot examples, you could include 10 or 20 examples in the prompt, but now you have more input tokens, and so that's the cost. And so currently that's the particular lens that you're looking at, the cost, correct? Is how many, like with this new optimizer in DSPy, it's going to be say, and then I also am curious like how it actually works into the metric. Is it, metric divided by tokens in the input? Like how particularly do you work in like a Pareto optimal? I suppose also I'm going to say I do want to completely unpack the box of the future of Pareto optimal. I don't actually understand it that well, so if you could maybe even just give us the beginning of how Pareto optimization differs from, say, just typical gradient descent and all these kind of things.
So great. So let's unpack this a little bit, right? So first of all, like your first question, how do we actually currently compute cost? What is this construct that we actually mean there? And when it comes down to measuring those, we actually mean token usage, right? Like just the number of input tokens time the API pricing plus the number of output tokens time the respective API price. And while this is of course not perfect, right? Like because costs might change over time. They might differ depending on who actually uses the model, right? You can host, for example, certain models that are open even on your own hardware, right? So there you might want to have a different cost calculation in order to then judge which agents to actually deploy in your setting, or which agent is on the Pareto frontier for your specific pricing. And that is something, right, that is not easy to do. The way we have overcome or think about it, this problem is that we think that evaluations must be dynamic. So what do I mean with dynamic evaluation, right? Like while, benchmark accuracies or like a core feature that was very important in the past for benchmarking models or even machine learning models in a more traditional sense was that benchmarks and the results should be the same when I run the same model last year or this year or today, right? But for, this more cost-controlled Pareto-informed evaluations, the results might actually change over time depending on how your cost changes. For example, how API prices change. So what we allow the user suggest in the paper is that they should actually choose their own prices for input and output token for any given model that is underlying as a backend model for a given agent, in order to compute the Pareto frontier that is right for them, right? That is kind of that matters for them. And how this is implemented in the very simple DSPy optimizer that we mentioned in the paper is basically just as a multi-objective goal, right? Where you look at not only the accuracy that you get on a small development set, but also kind of the total count of tokens, which is then translated into the dollar cost. That's all it is. Yeah.
So with the Pareto optimal, so there's kind of like an exploit thing going. Let's say one achieves a score of 8 at a cost of $4, the next achieves a score of 9 at a cost of $10. Is it 90 versus 32? Like how do you scale? Like I don't even understand. Like, could you just take me through how the optimization problem changes? And I hope the question makes sense.
Yeah, no, absolutely. So basically what we're doing is we're implementing optimization in Optuna. Optuna is a library that can search through hyperparameters for any given optimization problem. And what it ends up with is, let's say we have, 200 searches through this optimization space to get to different types of metrics. So exactly like you said, we're sort of exploring the space of options we have with different few shot examples and with different, like what the different accuracies are for these few shot examples. And these are like, let's say we have 200 searches. So at each point in each of these searches, we basically start, let's say, from 10 given few shot examples. We take one out and we see what happens. If the accuracy remains the same, we continue down this path. If it doesn't, we switch to a different path and we keep doing this. So in some sense, it is finding a local minimum, and which is one of the reasons we said this is not like a very complex optimization method at all. It is literally just searching through the space of alternatives. And then at the end, you have, let's say, 200 points on this accuracy versus cost graph. You can see what the accuracy would be for a given cost. And the general principle is, and this is what the Pareto frontier looks like, is points that are above and to the left of any given point are better, strictly better than points that are to the right and below. Because if a point is above and to the left, that means that it costs lower while having a higher accuracy. So essentially, out of these 200 points, like out of these 200 hyperparameter searches, we can essentially find, let's say, the 10 or so points that are on the Pareto frontier that are strictly better than any other point. So we can discard the other 190 parameters, and each of these is, a set of few shot examples and a given prompt, and we can only focus on these 10. Now, once you have these 10 points on a graph, you can figure out what your specific trade-off is. So let's say you're in an application setting where cost is extremely important. You have a strict cutoff of like 5 cents per agent call. Then you can sort of see which is the agent which costs less than 5 cents and has the highest accuracy overall. And on the contrary, you might be in a setting where accuracy is the most important. So you can't do below 80% accuracy on a retrieval task. That's where you can sort of look at this Pareto frontier. And the key thing about the frontier is that it is like choosing a point on the frontier is always strictly better than choosing any other point that we searched for. And so that's why we sort of advocate for choosing points on the frontier. The other thing that we also found was there was a very low fixed cost to implementing this search. So let's say if someone did not implement this search over accuracy and cost at all, they would just go with the DSPy default optimizer, or maybe even just a model call. In that case, they might spend a lot lower on finding this set of prompts. So essentially, we have spent 200 model calls trying to search for the optimal parameters. It turns out, though, that this is extremely cheap. So it cost us like less than $5 to construct this hyperparameter search. And so in a production setting, when an agent might be used tens of thousands or hundreds of thousands of times, this we feel is like an extremely small cost. In fact, we calculate in the paper at what number of model calls does the variable cost exceed this fixed cost. And basically, you break even at about 1,000 model calls. So if you're using this like process to find your optimal agent, and you're using your agent more than 1,000 times, it's always better for you to first search for like jointly optimize for accuracy and cost, and then use the cost optimized agent than it is for you to just go with the naive agent. You can essentially always do better, especially in a production setting where you have more than 1,000 calls for any given agent.
Amazing. I think it's just such a powerful concept. There's kind of so much to wrap my head around with it. And I think like kind of thinking about Pareto optimal training and then Pareto optimal inference, these are maybe also sort of two different things a bit as well. And there's all this amazing work from like Mosaic ML. They had this chinchilla optimal compute, and they were doing it for pre-training language models. And I think how you're bringing these concepts into the sort of like new era of agent design is super fascinating. I guess kind of sort of staying on how this works particularly, I think it's just such a powerful concept, and I very selfishly want to understand it better, and I'm sure our listeners are trying to, weight these things. And so I'm curious about, and I also want to compliment your paper for the user interface. You link in the paper about showing here's the current cost of GPT-4, GPT 3.5 Turbo, and it's a UI, so you can update the prices. And now here's what the Pareto looks like for these different systems. Not because obviously the prices of all these things are changing constantly, and that's what makes another part of this difficult. So I really want to understand further, just like kind of the meta learning of the system. I hope that makes sense. Like if I'm testing these different models, I have my one system that's Llama 3 8B, and I see it gets to 80%. And there's kind of like this resource allocation problem now where my GPT-4 is at 85, Llama 3 just got to 80, but now I'm like, let me go spend more my training compute or my inference compute to see if I can get it further. So I guess I am on the inference, the training part. So then I'm thinking about, our last Weaviate podcast was with Krista Opsalong, who created MIPRO, and MIPRO is like language model is the Bayesian model. The language model is like doing the meta-analysis of what we should explore next. So I'm sorry this question is so sort of like indirect and open-ended, but what do you think about sort of like language models exploring the kind of, because you kind of like explore a Pareto frontier, correct? Like you have a promising candidate in a particular sort of category, and now you need to go explore it further.
Yeah, no, I think you mentioned a lot of interesting points, and also future directions for exploration there, right? So I think one key statement that we make in the paper that is corresponding to this like DSPy optimizer that optimizes not only for accuracy but also for cost is actually that we think that this is the start of a completely new design space for agent and also architecture search in that sense, right? What you call meta learning. So, I mean, if you look at the recent weeks actually or months, the field moves into even letting agents design other agents, right? So even optimizing kind of how these architectures actually look like. And of course, also with DSPy as the starting point, and you mentioned, the micro optimizer and the great work they're doing with that. Also the prompts. So not only the modules that are part of the compound systems, but also kind of what goes in and out. What do the instructions look like? How many few shot examples? What kind of few shot examples? And we have also obviously also thought about, okay, how can we actually be part of that design space? What could this look like? And I think promising ideas or directions that one can imagine is using, for example, the new frameworks like TextGrad, right, that kind of suggest these textual gradients for finding better prompts for optimizing a system. And you could imagine just writing a loss functions in this TextGrad framework that also incorporates kind of the overall length of a prompt that it searches over, for example, right? So this would kind of overcome this problem that usually, AI agents are built with like black box models, so you can't really, use these prompt optimization techniques that actually require a gradient, but you can use these like textual based gradient methods, for example, to find shorter prompts. And there's a lot to explore out there, I think. Excited to see what the space is going to do in this like new design space of cost controlled kind of agents.
Yeah, I love that point. I think like that automated design of agents, this idea that I could break up this task into 5 calls and then it's a cheaper model on each step. And then how does that compare to one call to say Cloud Sonnet? And I think that's like the territory that's super interesting. So I think this is still on this topic, but will transition us nicely into the work you've done on this evaluating the state of AI agent benchmarks. When I hear agents, I go right to thinking about tool use, particularly function calling. And so I'm curious if that's coming into the sort of still on this Pareto Optimal, like maybe how many tools each model is connected to is maybe like this one has 8 tools, but as a result, it has a longer input prompt because now you need to describe all these tools. Or then also maybe it's inefficient because it's maybe how many functions can it call per step is a question. Can you do 2 or 3 function calls? So I'm just curious, has kind of function calls and tool use, has that entered you're thinking about these kind of things?
Yeah, that's a great question. So we do think of Pareto optimizations for AI agents when they have tool use and other capabilities. I think the way we're thinking about it is slightly different from what you described. So I think you mentioned that we have like the number of tool calls or the number of function calls. But where we instead ended up on was we only look at factors that are relevant from a downstream developer's perspective. So let's say I'm a downstream user, a downstream developer looking to use an agent to automate some part of my pipeline. I actually don't care how many tools it has access to or how many function calls it makes and so on. What I do care about, though, is how much it costs to get a certain level of accuracy. So I think at the end of the day, we always boil things down to cost as the lowest common denominator. And so as an example, let's say if we are using agents to solve SweBench. SweBench is this wonderful benchmark created by our peers at Princeton University that aims to solve open GitHub issues using language models and language model agents. So let's say if I'm trying to use SweBench, I might give my agent access to a few tools. I might have to host it on a certain VM, let's say on a Microsoft Azure VM. I might have to enable certain Azure services, let's say access to a hard disk, access to certain natural language APIs, and so on. So at the end of the day, what we use for evaluating the Pareto frontier there is the total cost, the total average cost of an agent to solve a task on SweBench. And this includes everything from the cost of running the VM instance to the cost of renting the hard disk space on Azure to the cost of language model calls to the API and so on. Because I think at the end of the day, we have to sort of think about it from a very developer-centric perspective, which is how much does it cost to get a certain capability from a given agent. And then I think this also enables apples to apples comparisons between agents, because if one agent uses 100 tools or has the capability to use 100 tools, but it runs extremely cheaply, I think that would be far preferable to another agent that uses just 3 tools. But each of these tools costs like $1 an API call. And so to solve one GitHub issue, you're spending like $100. So I think boiling things down to the cost control, like the US dollar cost control perspective, literally, has been helpful in figuring out how to compare agents on an apples to apples basis.
That almost like kind of opens, for me, it makes me think about sort of the like agents that sort of like do research that's not necessarily just tied to the inference. So let's clarify that. Like if you're doing web search and you're building up an index of information and then you're going to use it later, it's not necessarily limited to this one inference. And that's kind of like where the lines blur to me between, I guess it almost makes you think about MemGPT at Weaviate. We're working on this thing called generative feedback loops. It's like save the outputs of LLMs or agents back in the databases. And it's, yeah, so it just really, like you might say with SWE Bench, let me train a specific model for this one task. And now you're like training this model that's more efficient, but not really part of this one inference. Yes. So yeah,
Exactly. And I think that's where the fixed versus variable costs come in. So I think for all of these specific optimizations, you would have a fixed cost. The fixed cost could be in terms of the specific optimizations that you want. It could be to crawl the web and build a search index, and so on. And the variable cost is the cost of running an agent on a new task for the first time. And I think, like, as long as the fixed cost is low, or as long as the downstream agent has to be run like hundreds of thousands of times, for instance, I think in the long run, the variable cost will always dominate the fixed cost. But if we are in a setting where we only need to run this task a couple dozen times, then I think the fixed cost becomes the dominating factor. So I think this distinction between fixed costs versus variable costs can also be clarifying in terms of how much an agent costs to run.
outstanding. And I think as we talk about agent benchmarks, I'd like to maybe anchor with this sort of like LLM as DBA and as like a database agent, and then also how that database agent concept might change with machine learning models, training machine learning models, working into the picture of what a database manager might have to do in the future. So maybe even Sayash, if you wouldn't mind kicking this off, because I also, as I was reading your paper and learning more about your work, I thought it's super interesting that you're writing a book, AI Snake Oil, and I think it's just perfectly themed with the second half of this paper. Sorry. Actually, what I would love to kick off with is if we could talk about the long context versus RAG evaluation. I think with Weaviate vector database, this would be a good one. I read that. I hadn't actually been keeping up with these papers, but when I read that nugget from your paper, I was like, oh, nice. I'm glad to know that. Would you mind explaining that?
Yeah, sure. So what you're referring to is our experiment on a little section where we kind of analyze the specific case of the novel QA benchmark, which is a benchmark that is specifically designed to kind of evaluate long context language models. So, language model over the last couple of months have, gotten increasingly large context window, right? So the question is now, okay, how do they actually work on question answering tasks with like long input documents? So for example, novels in this specific instance. And what the analysis that we do in the paper there is that we actually use novel QA as an example of how a benchmark can be misleading for downstream, deployment decisions. And the point there is that the way novel QA, rightfully kind of evaluates different models is by putting not only the entire novel in the context window, but also all of the questions. So sometimes, these are 10 to, I think, around 30 questions per novel, that the model is supposed to answer all in one go with the same output. However, this is not really how Q&A would work, in the downstream setting, where a user will not ask all of these questions at once, but sequentially. So actually, if you would deploy such a model in, the downstream setting, the cost would be orders of magnitudes more, because the novel is passed into the model as context, right? Like for every single question again. And there we kind of just showed that in this sequential setting, where the questions are asked individually, there actually RAG, outperforms the setting that novel QA analyzes by a lot in terms of cost, while achieving almost the same accuracy, right? Because obviously with RAG, right, you retrieve the necessary content for each given question that comes as context, and you're not passing the entire novel into the context window. So there, while there's nothing wrong with the novel QA benchmark, this is just an example of how, if now a downstream developer would look at the novel QA leaderboard, where RAG is not even, RAG agent does not even appear because of the specific setting they evaluate on. This would be misleading in terms of what kind of agents would perform well in a real world scenario where a user might have questions with a long context document.
Yeah, it's so interesting. And I'd say I do sometimes when I'm talking to chatbots, group a few questions together. I'm sure you both do. So I think it depends on the scenario, and then kind of transitioning perfectly to sort of AI snake oil and all this that claims. People make these claims, and there's all these benchmark wars and all this kind of stuff. So can we maybe transition now into AI agent benchmark? I'm so curious, just sort of the evolution from MMLU to now you're benchmarking an agent. And I love the anecdote of it's tasked on navigating web pages, but what if the website changes, say documentation for code or what have you, and then you have these new categories of generalization. Kind of reminds me of Francois Chalet's on the measure of intelligence. He had these like broad, narrow generalization, and you've done a really amazing job of extending that to agents. Could you dive into that?
Absolutely. Yeah. So one of the things we found when we were looking at agent benchmarks was that when developers develop agents that are doing well on these benchmarks, the claims about how well these agent works can be very broad. So for example, you might have a developer sort of achieving state-of-the-art performance on a web agent benchmark, let's say Web Arena. This would be accompanied by claims that this agent can sort of has broad domain general capabilities on the web. So it can take autonomous actions on the web. And even the developers of Web Arena promote their benchmark as this test of domain general capabilities. But if you look into what Web Arena actually does and what websites it has, it turns out that all of these websites have like a very sort of fixed static schematic. So for example, the way Web Arena works is you have clones of, I think, about half a dozen different types of websites. There's like a Reddit clone, there's a GitHub clone, there's a clone of like Google Maps. So I think it has OpenStreetMaps. There's a clone of Wikipedia and so on. And the tasks are like an agent has to sort of take a certain action in this fabricated web environment. So it could be tasked with creating a new post on the Reddit clone, or creating a pull request on the GitHub clone, or searching for something from Wikipedia, or finding the directions to some place using Google Maps. And essentially, if you look at all of these websites, unlike the real web, where tasks can be open-ended, you might click on a link and go to something that's completely unseen. You have like a very structured way of solving queries. So, for example, on Reddit, let's say a user wants to post something, you might even be able to hard code how something can be posted. So you might hard code the fact that an instruction to an agent is click on the UI element titled create new post. It might even be hard coded into the URL. So if the task is to go to a specific user's profile, you might hard code something like go to or add /user/username to the end of the URL. Now, all of these hard codes are very useful for getting a higher score on Web Arena, right? Because Web Arena is this sort of self-contained environment where nothing is changing over time. But say you were to deploy such an agent on Reddit. At first, it might work very well until one day Reddit decides to change the UI, to change what was earlier called new post to create a post. And then your entire hard-coded sort of setting breaks down. And I think this was the crucial insight that sort of led to a lot of our analysis in that section, which is claims that an AI benchmark is measuring domain general performance are misleading so long as you don't have a held out test set at the right level of generality. So what do we mean by the right level of generality? We sort of have this hierarchy of 4 different levels of generality when it comes to agent benchmarks. So at the beginning, at the bottom of this ladder, you have distribution-specific benchmarks. So these are benchmarks that you only expect to use in distribution. You're never going to encounter an out-of-distribution example. This could be something like, I don't know, grade school mathematics. It hasn't changed for the last 3 decades. We don't expect it to change anytime soon. At the next level, you might have task-specific benchmarks. These are benchmarks where you expect out-of-distribution samples, but the task itself remains relatively the same. So for instance, for SWE-bench, you might expect that the types of programming languages we use 5 years down the line changes. You might expect that the types of frameworks people are using 5 years down the line changes. 10 years ago, no one used PyTorch. Today, it's the de facto framework for building machine learning applications. And so essentially, these are things that change over time. But the specific task of having this description of a programming issue, having a repository of code, and then trying to implement a patch to fix this issue, I think this overall task is relatively stable over time. So this is an example of a task-specific benchmark. And the way to create a held out test set for a task specific benchmark is to introduce distribution shifts. So let's say you have tasks from a certain distribution already released. You might also want to add a held out test set that's never seen by the agent developers, which has tasks that induce this distribution shift, maybe by using a different programming language, maybe by using different sets of repositories in the test set compared to the train set. And this is to avoid agent developers overfitting to the training set. The third level of this ladder is a domain general benchmark. So this is something like Web Arena, which claims that it tests general purpose web browsing capabilities. What's different for domain general benchmarks compared to task specific ones is that for a domain general benchmark, there might be different tasks themselves. So there's no longer just one specific task, like solve a GitHub issue. On the web, someone can order something on an e-commerce website, look for directions from different places. There's navigation, there's information retrieval, and so on. And so for this type of benchmark, what you really need in the held out test set is not just different distributions, but rather entirely new tasks. So for instance, one way to fix Web Arena, in our view, is to create a held out test set that has completely different tasks from the training set. So a model developer or an agent developer can do all sorts of optimizations, all sorts of hard-coded stuff on the train set, but they don't know what's in the test set. They don't know if there's like a new website, if there's like a different kind of platform. Say they introduce like a new social media platform, like a Twitter clone, or a completely new type of website, like a Notes app or something. I think that would be the appropriate way to encounter and to measure for this type of generalization. Because the claim is that this type of agent can generalize to new web domains. And then finally, I think at the top of this is what some might call AGI. I think we call it general purpose or like cross-domain general purpose benchmarks, which is essentially an agent that's trained to solve web tasks, also being able to solve like robotics tasks, also being able to solve, like coding tasks. It's like fully general purpose capabilities. And I don't think we're at the point yet where we need like this type of benchmark. I think we're quite a bit far from that point. But when it does come to that, I think the way to test it out is for these benchmarks to have held out domains. So there's an entire domain that, the developer of the agent does not even know what that domain is, but you need to have tasks spanning the entire domain in the held out test set. And that's how you sort of measure that generality. So I like to think of this framework as sort of building on and in some sense complementary to Cholet's framework of narrow and broad intelligence and generalization. Because I think while Cholet sort of focused on generalization as a measure of intelligence, I think we look at it a bit more instrumentally in the sense that we are only concerned with how well a system works, irrespective of whether it is actually intelligent or not. It's completely fine from our perspective to hard code all possible scenarios as long as you can do well on this held out test set. It's completely fine for an agent developer to implement some sort of search, scale up inference time compute, do all sorts of things to achieve high benchmark performance. What we really care about is that this held out test set should reflect performance in the real world. And I think that's the sort of main construct that we are interested in.
Yeah, amazing. So many interesting ideas in that. And I guess, so it really inspires me to just think about how do we measure the most powerful AI system in the world. And then I sort of see that as kind of like counter to the first half of our podcast about the cost optimization, where I see, most of the developers that I've seen working at Weaviate, building things with Weaviate, they're like there's like some super specific thing that they're crafting it to. And so I see these as a bit different, but I guess like just what I'm inspired by listening to all that is is like adapting to new tools, new environments. And I guess I'm curious what you think about multi-agent systems, and maybe that's kind of what induces the distribution shift of the like you mentioned the suddenly a Twitter clone. I love how it's suddenly a Twitter clone because it's still like in this benchmark world rather than like new Twitter. But yeah, so I'm just curious about this like multi-agent perspective and maybe like what the distribution shift might be. I hope that makes sense. Like for example, we're three agents in this world of AI research, and we used to use PyTorch, and now say DSPy comes, and we're like shifting to this new tool. And so maybe is it like new tools? It could be like new methods of communication. I guess maybe just like what are the distribution shifts for the most powerful AI systems in the world?
Actually, I think this gets at a nice point that is related to the example that Sayash gave with the specific policies, right? That an agent developer can craft into the agent that might work well, like literally give natural language instructions for a task like create a new user profile or, order the shampoo I ordered last month again, please. Because you can think about not only as how general an agent or a multi-agent framework is, and how well it generalizes to new tasks, but also how adaptable is it, right? Let's say there's like a new tool that we want to add to an agent, right? Like is it as simple as is the framework as general and kind of the existing agent, the existing system general enough to literally just connect it and then directly profit from it, or does it actually take significant effort to adapt the agent to this new tool or adapt the agent to this new policy that I might want to add to the prompt in the first example. And I think this is something very relevant for downstream users, right? That might deploy such an agent, and I think is maybe even in the short term at least more valuable to think about this kind of this adaptability of multi-agent frameworks or multi-tool frameworks. For given that there are new tasks that kind of come along, right? That the agent might encounter. In terms of what these distribution shifts look like, I think good examples are can be found on the one in the paper, but can be let's say there are new Python libraries, right? That my software engineering agent now needs to use, or I want it to use. And of course, like if there is web access or the agent has a tool kind of in order to query the web, it might find the documentation and learn to some extent from that. But it might also be necessary or even like or beneficial to kind of adopt the existing compound system, train it in some sense, right? Like it's not clear what this means, on the new Python framework that I might now face tasks of. Or about, and then kind of adapt the agent in that sense. So there are all kinds of distribution shifts that you can think about. It depends a little bit on what the agent is used for, and then what kind of step of the ladder in these four ladders that Sayash just explained we're talking about. But yeah, I think these are just some comments on that.
I think one thought experiment that Benedikt and I like to run through is like to create a web agent benchmark that would automate like half of the work that we do, or try to automate like a lot of the web browsing that we do. I think we would just keep a list of all the websites we visit in a day, right? Like, so we visit, I don't know, I think hundreds of websites every single day and navigate these links in like a very proficient way, if you think about it. And so an easy way to develop such a benchmark might just be to, just, I don't know, annotate all of the tasks that you've done in the last 7 days, and then try to use any of the agents that are state of the art on things like Web Arena. My guess is these agents would be able to solve like less than 10% of the tasks, even though they claim an accuracy of over 40 to 50% on Web Arena. And I think that really sort of gives an example of how simple these distribution shifts can be. Like, even though Web Arena looks at 8 different domains, I think that's still not enough. And I think we do really need to have held out test sets that have never been seen by these agents to get an accurate measurement of what their accuracy in a real world task would be.
Yeah, it's so fast and so many exciting ideas about how to measure AI systems. I've always found this kind of like domain, like what is a domain of data, to be sort of esoteric. Like you're talking about basketball and now it's baseball, or now it's about gardening. So it's like totally different, and trying to measure that. But I love this kind of thinking about the tools, or yeah, I guess the tasks, even kind of like, so now you're answering questions. Oh, well, now you're summarizing documents, and that kind of perspective on it. I guess maybe kind of one more question I wanted to have on, I love this kind of like building this into DSPy and making this an easy optimizer for people. And I'm curious if there would be, I'm curious what you think about the general kind of agent design. If you have sort of the smartest model possible that sort of orchestrates all these other models, it's something that I think is pretty powerful, where you have specific agents for specific tasks, and then one kind of, sort of the orchestrator agent. So I guess I'm curious if maybe that has some connection to the orchestrator agent is designing how specific each of the models are. How much generalization do I need for each of these submodels that are going to be cheaper? Because isn't it, if it's going to be very general, it's also going to be more expensive, probably. So yeah.
Absolutely, yeah. So for some of these tasks that we look for in like real world settings of interest to downstream developers, the tasks are very, very specific. So if the tasks are specific, then I think it's enough to use DSPy even on a cheaper model to optimize the variable costs, basically, let's say by doing like a lot of search over different possible future examples and prompts and so on. And that's actually already good enough for a number of business use cases. Then we have settings where things are a little bit more general. So there, I think we might want this sort of manual orchestration. So you might want like essentially what is essentially like a long list of if-else statements. If you're in this domain, try to use this agent and so on. And I think the type of agent orchestration you described is probably like at the last end of the spectrum where you cannot have this list of agents on its own. And essentially, I think that's where the modern tool using documentation comes in very handy. So models like Claude 3.5 Sonnet can use hundreds of tools, and it's not really a hierarchical sort of thing. You can basically just specify all these 100 tools in a doc string, and that's actually enough for it to be able to use these tools. And I think that's where that type of tool call can be useful. So you might have a tool call for your specific purpose-built agent, and then let an LLM like Claude 3.5 Sonnet decide what sort of tools to use. The problem with this type of general purpose orchestration, though, is that currently we don't really have reliable ways to do this well. So I think one of the major hurdles for AI agent use in the real world is that even if a language model or an agent is capable of doing something, and by capable, I mean, it could in theory solve it if given enough tries, it's not reliable. So it does not get it right all the time. The answers vary depending on because of stochasticity, because of a lot of other factors. And so what that means is, as of right now, I think a lot of this type of general purpose orchestration has just fallen flat when it comes to the real world. So we've seen examples of major product failures. So we've seen examples of the Rabbit R1, the AI pin that was supposed to be sort of strapped onto your T-shirt. We have seen examples of a lot of wearables go awry simply because we lack this type of reliability for. And I think, like, to be clear, this is definitely something that varies from use case to use case. But specifically when, let's say, you have consumer-facing applications like the Rabbit R1, and it only orders your Uber Eats to the correct location 80% of the times, that is a catastrophic business failure. So in order to get to real-world utility, it's not enough to have like 80% accuracy on these tasks. And I think that's why we haven't yet seen this type of high-level general system being adopted in real-world use cases. Think we need frameworks like, we need to have 5 nines of reliability, like we need to have 99.999% accuracy in order for these systems to be useful. And if past experience is any guide, for instance, from self-driving cars, the capability to drive cars on roads in like a reasonable way has existed for a decade at this point. And yet self-driving cars are nowhere near being commercialized. I mean, we do have Waymo, which seems to be the standout, and yet Waymo has only driven on 2 cities in Phoenix and San Francisco. It has no freeway miles yet. And so I think we still have a long way to go. And that's when the technology is already a decade old. And I think we should sort of prepare ourselves for a lot of the work in the next sort of year or two, or in maybe like even the next decade, to be about adapting to specific tasks and specific domains rather than dealing with general purpose technologies that can, orchestrate irrespective of what is thrown at them. And I think the more constraints we have in the user setting and the user experience, the easier it'll be to design useful agents.
Yeah, amazing. And I'd love to sort of do on that, to stay on that, to promote people to build things with Weaviate and, and to build their specific use cases. But yeah, it's amazing. So kind of that reminded me of one other nugget from your paper about the integration of human feedback and optimization. And you sort of think about this Uber example and the Waymo, maybe the Uber example. I always, when I hear about agents purchasing things, that's never made sense to me. I think you always want to see like one more time, okay, before you just buy my flight to, Princeton or whatever. So maybe quickly, if we could expand on integrating feedback into optimization, human feedback, and just, I guess, with the state of that, because even just having a chat with a chatbot, especially with generating images, right? You're say, hey, no, I mean more like this, and you don't even really know the language to use, especially with images, and you're trying to like come up with the design vocabulary on the fly. If you're like me and you know nothing about design terms, but yeah, how do you see the integration of human feedback with optimization?
Yeah, no, I think I'm personally super excited that I see that many of the also industry applications, let's say industry products that are made, are actually targeting at that niche, right? Where an agent is always seen as kind of, or an agent that is always coming together with an interface for a human to oversee, to have like some observability about what the agent looks like, not only during the development, but then also later during the actual deployment. And that enables kind of a human worker to obviously oversee multiple agents that might solve multiple tasks in parallel, right? And then kind of intervene whenever there's a problem, or literally ask questions when an agent asks for help. And I think why I'm so excited about this are actually two main reasons. The one is capability. So, for example, we see, let me cite the example of a benchmark called UserCo, which is on the USA computing programming Olympiad tasks. And there, what the authors did there is actually is that they used problems that none of their agents that they built for the paper were successfully solving, and then just did a human uplift study, or like a human a guidance study. I think that's what they called it. That where a human has up to 5 chat interactions with the agent in order to give hints. Okay, like this a suggested solution might fail because there's some indexing issue, etc. And that actually led the agent to achieve from 0% on these like examples that none of the existing agents had solved, up to 86%, which is an immense lift, right? An immense boost in capability, which is super exciting. So what kind of can human in the loop oversight achieve, and not only in terms of capability, but also in terms of security, right? So kind of mitigating downstream harm and kind of catching these catastrophic or consequential failures. And the second thing is related to that, which is actually cost, right? Because while it is not clear in terms of reliability, right, what is the human baseline? Obviously, humans also make errors, right? So, but then the question is, how costly are these errors? So how consequential are they? There are other, intersections with also like accountability. So, if an agent makes a failure versus a human, obviously there might also be different legal implications that I'm not an expert on. But we think about this as cost. So obviously there's heterogeneous cost to failure, right? So certain tasks in this example you mentioned for a travel assistant, right? If there's let's say a flight booked to the wrong city, that might be much more expensive than just having a typo in a name change of a passenger, for example. And kind of integrating that into how we evaluate agents. So what are the kind of the type of errors that an agent makes versus a human makes, and then also how does this change if we have actually humans in the loop, in terms of mitigating kind of the overall risk in terms of financial error if we deploy an agent in practice. So this can be this can make sense from the reliability point of view in terms of minimalizing errors and cost of these errors, but also in the safety point of view, where we want to definitely avoid some of the really consequential failures that cause downstream harm.
Amazing. I've loved this discussion about benchmarking, and now thinking about human in the loop benchmarking and this the human error that could be present. It's such an interesting topic. I've loved reading this AI agents paper and discussing with you both this. These two things of the cost performance optimization and also just the state of benchmarking that just motivates you to I guess every time you think about the state of benchmarking, you think about what does it mean to be the most powerful AI, whereas AI ahead, it just kind of naturally leads you that way. So I kind of want to anchor this question to ask you both broadly. It could be future research you're intending to do, or just maybe more broadly in AI, sort of what directions for the future of AI excite you the most?
Personally, I'm excited about the field switching towards reliability as a top line metric. I think in the last few weeks, we've seen many proposals about improving reliability. So, for example, if an agent is unable to solve a task and it takes the wrong answer, that's much worse than if an agent is unable to solve a task and it abstains from answering. It says, I don't know. And I think we've seen work that tries to get to this point of improving reliability in this sense. That's really exciting for me. I think given that the community's energy, and even in companies, the energy is really increasingly turning towards these compound AI systems. I hope that this becomes sort of a key direction. That's definitely something I'm very interested in working on in the near term. I think that's definitely one part. The other is a focus on honest evaluations and benchmarking. So, as we speak on this podcast, there's a huge controversy on Twitter about this model called Reflection 70B, which is a fine tune of Llama 3.1 70B. And almost the entire controversy revolves around gaming benchmark scores. So while people have taken benchmarking and issues with benchmarking seriously in the past, I think this is really having its moment right now. And so my hope is that this sort of cascades into increased attention on really all of the issues we describe in our paper, because I think these issues have been around for a while, but it really requires the community's attention to these issues for it to make an impact. And so I hope that people find our paper meaningful in terms of dealing with these issues and figuring out what it means to have good benchmarking practices.
Yeah, so obviously I'm also super excited about reliability and kind of how we build systems that are reliable out of inherently stochastic components, which language model I think for the time being will remain. I think that's something that we've also seen in other fields, right? Like people in physics and in adjacent fields have, I think, a lot of experience with that, and it's just super excited to explore how can we maybe learn from these other fields and kind of incorporate the findings and the methods in order to also build more reliable systems with language models. I think just a small addition that I'm also in addition to that I'm excited about is kind of breaking up the wall between models, like treating them as static kind of backend models that we then can use into compound AI systems, but also fine-tuning them in terms of updating the weights to make them specific for compound AI systems, for agents. So this can reach from having models that are specifically trained to do better search, to find better solution in a setting where we can actually verify a solution or not. So we can retry with the same model, right? We can search for a correct solution. But this also goes into models that are specifically fine-tuned to maybe produce certain outputs within the compound AI system. So be really good at this specific retrieval step from this specific database, and kind of leverage also the full power of fine-tuning the weights, not only the prompts.
I find that one to be so fascinating, of whether I'm sort of in the camp of we prompt tune Llama 3.18b, and that's kind of like our smallest language model, and I'm not quite in like the knowledge distillation camp. Sort of actually for the exact reason of this kind of robustness, reliability thing. I worry, like if you do this knowledge distillation to a 300 million parameter model, that's your search query writer, like it's like the multi-hop RAG example, and this writes queries, but it's a smaller model. I worry that it's not as robust to the distribution shift as just and not as easy to then update, because if you're just updating the prompt to give it domain knowledge, then it sounds easier to update it. But yeah, so I guess if we could just stay on that a little, like, what do you think about that knowledge distillation, smaller models? Are you all into that, or did that maybe agree with my counter take to it?
I think it depends on the scale and also the generality of the problem we're solving. So, like if we're on like the first level of the ladder that we discussed, if you're only interested in distribution examples, I do think smaller models can be pretty capable. On the other hand, if we're in a setting where we want adaptability over time, so let's say we want to keep updating the prompts, we want to keep updating how the model behaves, I think it might be worth using a slightly larger model. That said, I think Gemini is a great example of how distillation is actually like pretty helpful in a certain sense. So we do have like a general purpose model, essentially Gemini Flash, and actually also Gemini Flash 8B, which is a smaller version of Gemini Flash, also distilled from it. And both of these are in some sense like general purpose enough, I think, for the types of tasks you described. And yet from everything that we know about distillation, they cost orders of magnitude lesser in terms of the overall compute needed to train these models compared to if we try to train them from scratch. So if we sort of compare in an apples to apples way, like let's say if here the comparison is on training compute, then my bet would be on distillation probably being as effective, if not more, in terms of the downstream model performance we get. But definitely, like if the comparison is between like an 8B general purpose model versus like a 300 million parameter model, I think the 8B model will come out ahead most days of the week.
I really like that dimension to it of adaptability might be easier, but the cost is definitely going to be better with the smaller fine-tuned model. And I know you two are the worst person to take the counter argument to that. It's trying to optimize the cost of it. And yeah, it's also amazing. I want to give one more mention to Ophir Press, also at Princeton, who had come up with that test of giving language models really absurd questions. And instead of saying, I don't know, they would always answer the absurd questions kind of. So yeah, that's a really interesting nugget on the say what they don't know. It was Sayash and Benedikt. Thank you so much for joining the Weaviate Podcast. It's such an interesting conversation. AI agents that matter. Such an amazing paper, and I'm so impressed with all the work you're doing with the Princeton Language plus Intelligence Lab. I think I got the two words right, correct together. Thank you so much for joining the podcast.
Absolutely. Thank you so much for having us.
Thank you so much.